Machine learning is fundamental to artificial intelligence, so we're going to take an intuitive look at it with as little math as possible. Neural networks are fundamental components of many AI systems, including large language models like ChatGPT. This diagram here looks at a single neuron. Each neuron has some number of input values. These are data points that represent the different features of your domain. Each of those gets multiplied by a weight. And the weights are initialized to 0 or some arbitrary starting value, and then they are learned over time. You can think of them as a factor of how important is this input value or feature to the eventual answer. The algorithm adds all of those together, and then that value goes through an activation function. The first thing we're going to look at is a perceptron, which is one of the original AI algorithms developed. And that just classifies something a binary true, false, or class A, class B. So in that case, the activation function, if it's a 0 or a negative value coming out, we're going to say it's one thing. If it's a positive number, we're going to say it's the other. But in general, you are going to be doing supervised learning on these networks so that you have training data, you know what the answer is, and on the bottom here you have the desired value D. So then you can look at, okay, well, what was my error? Did I get the right value, or was I off by some amount? If you have an error, then we're going to go back and update those weights, and we're going to repeat that process until we've trained our network to be as accurate as possible. So let's look at a concrete example. We'll take spam filtering. And for simplicity, we'll just start out with two different features. So we're going to have two input variables. The first is the frequency of keywords that we'll say are associated with spam. You have some examples here, the word win, free, or click. The other dimension or feature we're going to look at is how many external links or attachments are in the email. So that's our input data. And then the classification or the output that's going to come is either it's a class 1 or 2. It's either a legitimate email or we think it's spam. We're starting out with just 2 dimensions. In most real world scenarios, there are many, but 2 dimensions is about the most, maybe 3 that we can easily visualize in our mind and kind of wrap our head around. But let's use this as an example. Here we've just defined our algorithm for our use case. We have our 2 inputs, x1 and 2. You can think of that as a function that's going to come out with a binary answer, spam or legitimate email. Now keep in mind, our function, we're trying to model the real world. The real world we can think of as a different function, let's say H, where you have actual emails that are either spam or legitimate with those data points. So we're trying to approximate the real world as closely as possible. And the algorithm on the right side, we're going to take the sum of the input values multiplied by their weights, and then there's also a bias. Usually the weight 0 as corresponds with the bias, the weight is 1, so you just end up with that constant value. The activation function here, like I mentioned, if you have a positive value, we're going to say it's a spam category. Otherwise, we're going to say it's a legitimate email. This here is a graphical representation, and the perceptron, a single neuron, can only get a perfect solution, if you will, if the data is linearly separable, which in this case it happens to be. There are a bunch of data points there you can see which are really close to each other, but we are able to draw a straight line. Now it's going to find a dividing line if there exists one. That doesn't mean that it's perfect. That just means that for the training data we have, it is able to categorize them as either spam or legitimate. Let's take a look now at how we got to this point through a number of training iterations. Initially, our dividing line is on the x-axis, so as soon as we start to train, we make a big jump because we were far off. You're going to see some minor tweaks to the line. It's shifting just a little bit each time as our error is much smaller. We mentioned that a perceptron or a single neuron can only figure out a solution if it is linearly separable. If it's not, which many problems are not, you need a multiple layer network, such as the one here, which has 3 hidden layers. You have any number of inputs, and you can also have more than one output as well. Our perceptron example was pretty simple. Its activation was what they call a step function. It was either -1 or 1. Now, when you're looking at a neuron that's in the middle of a fully connected network, it often uses a different activation function, one that has a continuous output of values. Here are some common examples. ReLU is certainly common. You'll see that where if you have a negative value, you're going to output a 0, or then you get a linear output for positive values. Let's look at another example of supervised learning, this time with continuous outputs, not like our perceptron binary output. So here we have 10 sets of input values and the actual answer. So we have both the input and the answer. That's how we're able to do supervised learning. If you look closely, you can kind of see that the actual function here that is quote unquote our real world is z equals x plus 2 times y. So for example, in the first row, 2 plus 5 times 2, 10 equals 12. You can see that our model predicted 14.99, and you can see what the error rate is. So the error is simply our prediction minus actual, and you get a minus 2.99. We're showing the squared error value there also. We're going to explain that in just a second. So when you train the network, you run it through all of these 10 samples and figure out how far off you were. So the mean or average error here is minus 1.7, but that is actually underrepresenting how far off we are, because you can see in row number 7, where our error was actually a positive 6. We have another row, row 5, with a positive value 1.9. So we're actually farther off than that. That's why it's common to take the squared value, and then you can take the mean or the average of that, the MSE. So you can see those numbers there. So there's two advantages. One, by taking the square, you get rid of you really are getting the absolute error. You account for the fact that there might be negatives. The other thing that it's doing is the farther off you are from your desired value, you pay a bigger penalty, because as numbers grow bigger, the square root gets even further exponentially bigger. So that's why MSE is a very common error mechanism, and that is our loss or objective function. So on the lower right corner, you can see it's predicted minus actual, and that is the function we want to minimize. We want the error to be 0. So that's the goal when we train our system. This here is a graph of the mean squared function, which you can see it's a parabola, and you want to approach that point where you're at the bottom of the bowl, x equals 0. Now, it may look easy from looking at it here. You can say, well, why don't we just choose x equals 0? Remember that this function is an evaluation of the model. So there's a lot of other inputs. Keep in mind that neural networks have many, many parameters or weights. In fact, large language models have millions of parameters. So all of those contribute to what this error is. So now we have some error. The formula is shown here. What we're actually trying to do is figure out how much should we adjust each weight. So the first thing is that there's this learning rate. That is a small constant. So it's been shown that you want to take small steps in the right direction. If you take big steps, you might overshoot where you're going. You might miss a local minima or maxima. So you want to take small steps toward what you think is the right direction and continue to adjust. And this is why systems require many training iterations oftentimes to get to a good solution. Now, how are we going to adjust each of the weights? So this formula may look a little complicated with that right-hand term. What it actually is, so this is a partial derivative, and I'm going to switch to the whiteboard here so we can illustrate what that is. Okay, let's say we've trained our network, and our current error where we're at, let's say, is right there at that dot. So what the derivative is, it's the rate of change. It's the rate at which, when we change one of the weights, what effect will it have on this error value? So you're essentially calculating the slope of this line that's going down this way. So I'm sitting here and I want to know that if I change one of the weights, am I going to go in this direction down the bowl? Now, as soon as I start to move this way, I'm going to be going off of the curve. So this is why we take small steps, and then once we get a little bit further, we repeat the process, and eventually we get as close as possible here to where our error is 0. We've minimized our loss function. So that was our quick, intuitive introduction to machine learning. Now, in our examples, for the spam example, we kind of arbitrarily picked 2 features, and then we looked at a pure mathematical example. In real life, one of the challenges is to figure out what should those input values be. What features of the domain can we capture data on, and do we think will be relevant to figuring out the underlying pattern? And then how do we represent them? Machines, computers, neural networks in particular, only understand numbers. So we need to somehow translate our input into a set of numbers, and they often get scaled down as well. So there's a number of challenges to figure out there. So I hope this has been helpful, and we'll see you in the next lesson.